Welcome to Spring LIB.
In this question, we are asked to calculate the magnitude of the angular momentum of the Earth in a circular orbit around the Sun, and we are asked to calculate the magnitude of the angular momentum of the Earth due to its rotation around its axis through the north and south poles. So this is two different types of angular momentum. In the first part, part A, we're going to be thinking of the sun as a point particle. And the reason why it is reasonable to do so is because the Earth is very, very small in comparison to its orbit around the sun. So if we're looking at the sun-Earth system, the Earth basically appears as a point particle, and we can sort of ignore the fact that it has actual dimension. So to calculate the angular momentum for a point particle, we're going to use mv cross r. And essentially, what this boils down to for a circular orbit is just mvr. So v cross r would technically be vr sine theta, but v and r are at 90 degrees to one another for a circular orbit. And so the angle between them is 90. And so sine of 90 is going to equal 1, and we don't need to include it. So we're just going to use angular momentum is equal to mvr. And we don't really know what the speed of the Earth is, but what we can do is rewrite v as 2 pi r over the period. So that's the distance that the Earth travels around the sun. That's the circumference of its path, 2 pi r, divided by the period or the time it takes to do a full circular orbit around the sun. So overall, we get the following formula. So we're going to just plug in our variables. So the m will be the mass of the Earth. The r is going to be the radius of the orbit, or the distance between the sun and the Earth. So that's going to be 149.6 times 10 to the 9 meters squared. And then that's going to be over the period. We know that the period is 365 days. It takes a year for the Earth to complete one orbit around the sun. But we're going to convert that into seconds because that's our standard unit. So 365 days times 24 hours in a day times 60 minutes in an hour times 60 seconds in a minute. That will get us our period in seconds. So once we accurately enter all that into our calculator, that's going to give us 2.66 times 10 to the 40 kilograms meters squared per second. So this is the angular momentum of the Earth due to its rotation about the sun, or its orbit about the sun. Okay, let's move on to part B. So in this part, we're asked to calculate the magnitude of the angular momentum of the Earth due to its rotation about its axis. So this is going to be a little bit different. Obviously, we're not going to be able to consider the Earth as just a point particle this time because the Earth is the system in this case. It's the only thing we're considering. So it obviously has quite a large breadth to it, so it's not a point particle. So in order to calculate the angular momentum for something like that, an extended shape, we have to use I times omega. I is what we call the moment of inertia. So it's basically an object's resistance to rotation, kind of like mass is an object's resistance to movement. And For different shapes, there's going to be different formulas for the moment of inertia. So for a sphere, such as the Earth, it's going to be 2/5 m times a squared, a being the radius of the sphere. So let's just go ahead and plug in our values for the Earth here. And the radius is 6,371 kilometers, or 6 million meters. So the moment of inertia for the Earth is 9.69 times 10 to the 37 kilogram meter squared. And then what we're going to do is we're going to plug that in to the formula. Now, omega is the angular speed, and we can rewrite that as 2 pi over t. So 2 pi over t, t being the period of the rotation. So very similarly to the previous calculation, for the period, we have to make sure that that is in fact in seconds. So, of course, the rotation of the Earth takes 24 hours. We're going to multiply by 60 twice to get that into seconds. And once we do that, we get a value of 7.05 times 10 to the 33 kilogram meters squared per second. So that is our angular momentum of the Earth due to the rotation about its axis. You can see that the angular momentum in part B is much smaller than the angular momentum in part A, and that's partly the reason why it's okay to consider the Earth as just a point particle in part A. So this is our final answer.